Hi, everyone. Um, thanks for coming to the talk. So my name is Chang, and I'm the VP of Engineering at Tubi TV. We're an ad-supported video on-demand service for streaming, and a lot of our stack is in Scala using Akka, and that's kind of why I'm here today across backend engineering, ML, and data engineering. Though I do have a confession to make. I'm actually in a previous life, I was actually a Python programmer by trade. I was one of the early contributors to the pandas library in Python. I hope you won't hold that against me, though, and I hope you're still interested in this talk. So I'm here to talk to you about MLOps at Tubi, and really, there's kind of two sections to the talk, two main sections. One is want to talk to you about what makes MLOps different and really what MLOps is and what are the different challenges that we have to solve. And then I'll pick one aspect of operationalizing machine learning at Tubi that we've been working on in the past year or so, and that is making our ML models real-time rather than batch pre-computed. All right, so first, let's talk about what makes MLOps different. So really just what exactly is MLOps? It's kind of a nebulous concept, but my experience at Tubi kind of tells me that the only thing in common across all of the different definitions of MLOps seems to be it's just a bucket of things that our machine learning team feels that it's beneath them. Of course, I'm joking about that, but it means different things to different people, and it's fairly complicated. So let's take a look. This slide I stole from Twitter, and it tells how quote unquote classical programming differs from machine learning, right? So in this slide, it talks about if you're classical programming, you've got rules that are static and defined by humans, and then the software engineer will take those rules and then write them into code, and we'll run the program, and then as the input data comes in, the rules will be applied and it'll spit out answers. And in this view, it goes machine learning. In machine learning, it's kind of flipped around, right? So instead of having this machine learning thing spit out answers, you're feeding answers into the machine learning, and the machine learning is telling you what rules to apply. Now, of course, this is a little bit inaccurate, or at least incomplete, right? Because when users log into the Tubi home screen, right, we are not shipping them a Spark pipeline.zip file and saying, hey, you figure out what home screen you're looking at, and you figure out how to render the images and start the videos, right? What we're actually doing is taking the rules that are coming out of these machine learning models and then feeding them into quote unquote a classical program, which is our production system. And so it's not that they're replacing one another, it's that they are working to supplement each other, right? So really, the workflow looks something more like this, where data, machine learning is spitting out the rules that then feeds into a production system, which then takes the data, spits out answers. The answers, in addition to being shown to the user, are then fed back into machine learning. And both kind of offline component and the online component needs data input, and this will become important later as well. The offline component of machine learning then breaks down into a couple of things, right? So we'll start with data, and then we have feature engineering, and then train the model, and then finally we serve it. So this is kind of the central diagram, if you will, that of how we architect our machine learning operations systems, right? So we break the workflow from the raw data all the way to operationalizing it and putting it in the hands of the user. And a lot of the architecture and how we think about the system revolves around this kind of breakdown to the workflow. So around this, I'm going to talk about three things, right? One is that there's an intrinsic feedback nature to this workflow, right? So if you remember, it's not so much that humans are coming up with the rules, it's this algorithm that's coming up with the rules based on the data that it's seen in the past, some time. And as that data changes, the rules will also need to change. The different features will go into models and it will produce different rules. And we'll need to tune the model based using different hyperparameters based on the performance that we have. And pretty much every component within this system will have a feedback loop that needs to be run continuously and monitored continuously in order for machine learning to be operationalized successfully. Right. Another big difference between kind of operationalizing machine learning and quote unquote classical software engineering is this aspect of research versus production. Right. So you probably have models that you develop offline in like Jupyter Notebook or Databricks Notebook or something that runs over large amounts of data in your features, and you might do that in Spark or similar system. And then you train your model, and then you also want to run that same model online, and you want to focus, and the features are also online, and you want to focus on, and there you're going to focus on having low latency, high throughput systems focused on getting serving a single user's needs rather than cranking through a lot of data, right? So you have this dichotomy of you need systems and representations of the model and the features that needs to meet different SLAs and different requirements, but you really shouldn't have to rewrite the same code, right? So I wouldn't really trust an ML researcher to write robust an Akka Streams service or Akka service, and vice versa. If I'm asking my distributed systems engineers to write re-implement machine learning models, high probability that an error will occur somewhere, and worse, these errors are probably just silent, right? So it might not even have an exception. It's just the model will not perform as well, and you won't really know why there's a difference between offline and online models. Right. Many of you probably have heard the joke, right? The old joke. There's two hard problems in computer science: naming things, cache invalidation, and off by one errors. And so my assertion here is actually we made an off by two error, because the hardest problem in computer science really is people. Right? And in other software engineering disciplines, the deciding on the rules and then encoding the system and running the system are generally the same people, or the same, at least within the same team. Whereas in machine learning, this workflow is actually split, right? So you've got data engineering that collects the data and manages the data warehouse or data lake, and then you give that to the machine learning team that does feature engineering, does model training, and that gets handed off to an application engineering team that's actually managing the serving and the production aspects of things. So each team have different skill sets, different overriding concerns. And so crossing that boundary is often when machine learning, ML ops or operationalizing machine learning fails in a lot of companies. Right. So those three things kind of encapsulates what I think makes ML ops really challenging and really hard. So let's take a turn and look at how we solve some of these problems. At 2B in particular, we'll talk about just one problem: how do we compute models in real time in the production system without having to go back and re-implement everything. Right. So first, some stats just to set the context. Over the past year, 2B viewers watched about 2.5 billion hours of content. So that gives you an idea of the data scale that we're working with and the request scale that our production system has. Roughly, we've run something like 200 machine learning experiments in the same time. So there's a need to iterate quickly and we can't spend a lot of heavy effort to coordinate across teams to make that happen. And then the third stat here is, we have a fairly small machine learning operations team, about 6 engineers managing the production system across all of our experimentation and ML services, right? So it also means that we need systems that can allow our ML team to run fairly independently and needs to be run reliably. All right, so for those of you who haven't looked at Tubi or haven't heard of Tubi before, we're a video streaming service. So one of the big use cases for machine learning at Tubi is personalized recommendations, right? So when you log on to tubi.tv and you'll see a home screen, this home screen actually represents the result of personalization by about 20 or so different algorithms. And then other aspects of the user experience are also personalized based on your tastes and your interests, or at least what Tubi's best guess is to be your interest, right? So we got featured containers, vertical ordering of the containers, the content ranking horizontally, and then other things like cold start, deduplicating content across the screen, and many, many more, right? So over the past year or so, one big challenge that we kind of solved, and it's really interesting, is a move from batch pre-computed recommendations to real-time recommendations, right? And this is a big challenge in operationalizing machine learning today. So for those of you who are not familiar, batch inference basically means, I've trained the model offline. For all of the known users, I just pre-compute what my recommendations are for them. Or if you're not working in recommendations, basically, you just pre-compute the predictions, right? Generally for those users. And we just shove those into a production database, some key value store. And the production system then doesn't really have to know much about machine learning, really. It's just, oh, I've got this key for this, that's the device ID. Okay, and the value is like, okay, what is the order of things that I should sort in? And it's pretty simple and it's pretty quick if you design the system and the data schema correctly. But the problem is, one, it's slow to respond to user activity because you can only batch predict it, let's say like once a day. It's also extremely wasteful. So if we're batch, you can't predict who's going to come back. So you pretty much have to just compute it for everyone. But really, you only end up using something like 5% of that data. But the main drawback to this is that for new users that are coming in, you can't pre-compute everything, right? So there's no personalization for new users, and that means every new user kind of sees the same experience, and we can't really show a Tubi that is a good fit for those. All right, instead, we want to move to the system where we're moving the model computation from this offline context where we're doing it in a Spark job, let's say, to online, right? So we'll move the features to an online database, we'll move the models to an online database, and then when the user comes into the system, we'll compute the rankings and prediction for them right there and then within that request timeout, right? So this addresses the pain points that I cited about batch pre-computation, but it makes things a lot more complicated, right? Because I have to figure out how to ship the features to online. I have to ship the models. How do I actually do the models? Do the model computation online is a kind of a really complicated and big challenge, and that's kind of what we're going to talk about next. All right. So how do we compute the model? Well, what do we really need, right? So that to serve a user request with the real-time model computation, we need to extract the features out of the feature store online, transform them, and do a little bit of I would call it last mile massaging, right? And then we feed it into the model, and then maybe there's some post processing that's like a limit or some order by, and then we will respond. right? Because it's in the critical path, right, for the 2B user experience, we need to meet some pretty strict SLA. So the model computations need to finish in like, 1 or 200 milliseconds, because we don't want to keep the user waiting forever. And moreover, because we want to allow the machine learning team to iterate, the system needs to be very extensible. So we can add new transforms, we can add new models, and all of that without too much involvement and hand coding. Right? And then the last requirement here is, obviously often offline and online have different requirements. So we need different data sources that are fit for each use case. So whatever this model computation system will need, and needs to also be able to get data out of these systems. All right. So first thing we looked at is, all of our offline model development and data engineering is all done in Spark and MLlib. Natural place to look. MLlib pipelines. The problem is, research to production, like serializable pipelines, this is awesome. And it is actually really great for serializing pipelines that then you can use on other data sets, or from small samples to full data sets. But because you're down down to the Spark context, it's not for low latency serving, at least not in the kind of latency requirements that we have at 2B. The next thing we looked at are, kind of these all-in-one frameworks like Kubeflow that have KF serving, or like MLflow with MLflow serving, which I indifferently call this a, we write Flask code for you type of serving engines. One, it doesn't really fit into our stack, because most of these are Python based. It doesn't really meet our SLAs, right? Remember it's that the user goes to 2b.tv, and we want to show them a personalized home screen as quickly as possible. And obviously, it's also much more error prone because of the dynamically typed nature of Python. Moreover, in our experience, these all-in-one frameworks tend to be overly complicated. And really, we only need like 1 or 2 components. So we prefer to find specialized projects that do each component well. Right? A third option that we kind of considered is why not make everything in an embedding? And this is a common option in some companies where everything's an embedding. If you don't know what an embedding is, it's basically just an n-dimensional representation of the item that you're trying to rank. In this diagram, it's n equals 2, right? So I've got 2 diagrams here, and what you're trying to find is similar items, right? So if the user watched, item 1 or movie 1, we want to find other movies that are similar to this guy. And we define similar by this concept of cosine distance, which is the angle between these vectors. And it's very quick and easy to use a library like FAST or Annoy from Spotify to quickly find a neighborhood around the previous content, and we can rank by similarity, and we can get it going pretty quickly. The problem is that it's difficult to iterate. While it's easy to find the neighborhood around previously watched content, when the relative ordering of how you present that neighborhood to the user matters, it's difficult to kind of iterate on, or to control the relative ordering of that similarity through the embedding system. It's also hard to take into account multiple criteria, things like users multiple view history, or content popularity, or IMDb votes, or any other features, right? So this is a useful exercise, and embeddings are critical features, but it can't be the end-all be-all of kind of how we do real-time model computations. We landed on this project called MLeep, which kind of is it's both a serialization format and an execution engine. So you would write your models in the Spark context using Spark MLlib pipelines, or very similar. And in your Databricks notebook, for example, you would write code like this. I guess it's a little bit hard to see, but I'll show you a little bit, a demo in a little bit. And you can serialize this in the MLeep format. And then in your production system, you don't have to recode this pipeline, you just serialize it back. And when you serialize it back into the MLeep runtime, you're using the Breeze library under the hood to do the computation, so you're not bound to a Spark cluster, right? And this actually, we tested this out. It's really fast. Scala based, works well with our backend services, and it's also extensible. So if you want to add new operations, this is kind of how you do it. According to them, you add a pure Scala model of what the new operation is, and then you add the operations to both the Spark runtime, MLeep runtime, and then you register them in the operation bundles in both environments. Only problem is while this defines the transformation between the input and output, it doesn't solve the problem of how do I get the features, right? So what we found was that a lot of when we first started using this, we found that our ML team was spending a lot of time writing offline code in Spark to get the feature set ready for training, and then also then having to work with our backend engineering team to say, okay, I want to get this kind of feature set, but online, and some of these features will come from like the request metadata. Some of these features will come from this other feature set, and that even though we could unify the feature sets through a feature store, they still had to rewrite the code for offline and online context, and this really hampered their speed of iteration. So we kept the MLeep pipelines, and we added one small tool on top of that, which we endearingly called the Fed. So that stands for feature extraction definition. And I guess the engineer who wrote that really loved the Fed, and so we started calling him the chairman ever since, right? So basically, what the Fed is, it's a lightweight Scala DSL that looks and feels a little bit familiar to like the Spark data frame API, and it implements a very, very, very limited subset of these data operations. The query, as defined by the Fed, serializes to protobuf so that we can write it in the Databricks notebook and then execute it online. And it knows how to execute. It knows how to select data from the right context, and it knows how to run the different operations, both in Spark and also in our production system, right? So let's see a really quick demo here. And so hopefully this works in Databricks. Yesterday I was trying to present to somebody, and literally within the 10 minutes I wanted to do the demo, I could not log on to Databricks. So hopefully I'll have better luck today. I've named my cluster "Do Not Touch Me," so hopefully nobody in 2V terminates my cluster while we're doing this. Okay, so some imports. We've got a Spark session, and basically we'll show you how to run this in Spark. And so the idea is that we want to give our machine learning engineers a tool that is pretty familiar to what their usual tool is, so that they can kind of do this last mile coordination between the features that they want and then put it into the model or the transforms that we want. So here we're saying we want to read this table of features called batch daily recall titles, but it obviously could be anything. And we're going to select 3 columns out of this, and we're going to do some filtering and explode, right? So all of this feels pretty familiar if you're familiar with Spark. And then we're going to feed this into a transformer pipeline, which is the MLeep. Over time, I think the plan is that we can implement more operations in Fed itself, so that we no longer even need to have yet a separate thing, so that we can kind of replace the MLeep pipelines. But for now, we just integrate it so that we can run it. Right, and then some post-processing here, right? Sort by, and then a limit. So here we prepare the context manually, the execution context manually. But essentially what I'm doing is just generating data frames that represent my feature families. And when our ML team's actually working with this, we'll provide them with an API that kind of is in front of our feature store. So all of this mapping is done automatically, right? And then the Fed has this Spark runtime. We can just execute this query, which we defined. And so this will take about a minute or so, but it'll compute the results that we want and feed it, or get the features out, right? Filter it, and then put it through the model, that MLeep pipeline, and then gives us a data frame back. Right? And then while this is ongoing, we can also look at how we can run this in an online environment. I'll just show you how we can do this inside the same notebook. But basically here, I can prepare like a single request. So at 2B, a lot of our systems are, or most of our systems are gRPC-based APIs. So I just create a proto get ranking request, and that I add some device ID to it and some fake data. And all I have to do is say query, and then run it in the production context, and give me a result. Oh. Right. So here's the offline request, and then here's what the online result looks like. Right. So you can see it's actually not a Spark data frame. It's something that's made for single requests for online serving. And of course, there's some convenience here so that we can turn it back into a Spark data frame so that it's easier to just look at the results. So it actually looks kind of like this. So, offline, in the offline context, it's essentially just executing Spark code under the hood so that, it comes with the same kind of familiar workflows and performance characteristics. And online, it's using a combination of just pure Scala and the MLeep bundle currently. Right, and all of this finishes pretty quickly here. It's this is about 190 milliseconds. Usually in the actual production system, this whole thing finishes in about 50 to no more than 100 milliseconds or so. So it's fast enough for an online service. Okay. And let's just come back here. This language is also extensible, right? So it works similarly to MLeep, where if you want to add a new operation to it, you kind of write two implementations, one using Spark, one just pure Scala, and then you can just start using that new operation. And of course, we don't want to add like too many operations to this system. The idea is to have a small number of well-tested and common operations that are added, and everything else to be a composition of those things. And the last thing, of course, is that this language can be integrated across multiple data sets or data sources. So right, in the offline context, we'll want to access data from like S3. Internally at 2B, we use Redshift. Maybe also like a Spark catalog, so we can get our ML feature sets. In the online context, you want to get data from our online feature store, which we use ScyllaDB for, and then the request metadata itself, and then other services like for content, user profile, so on and so forth. Okay, but there's a bunch of caveats, right? So all of this is predicated on two key assumptions, right? So even though this API looks and feels a little bit like Spark data frame API, don't think of it as a Spark replacement, right? So the idea is that the heavy lifting in data should all be done during the feature encoding process, right? And then this is just so that we have some simple data manipulations that goes from this feature to the input, the direct input for the model transformations. So this assumption is critical because we don't want to have to re-implement all of Spark. That would be stupid. And another critical assumption is that in the online serving environment, right, the data volume for a single request from a single user is small. So we need to for a single request, we often need to extract multiple feature sets, right, and then join them together and then transform them. And these joins can be done in memory because the request is small. Otherwise, it severely limits the flexibility of the language and also the flexibility of the data store that we have. Right. Okay, so we kind of, as you saw from that progression, right? We kind of considered a bunch of choices, and we dove all the way down into all of the details about how to compute the model, how to extract the features, and we can come back up and kind of put it together. Right. So, what we defined really is a way to construct a model bundle, which is how we define our basic, ML unit, which has the input defined by this fed query, this model transformation pipeline, and some post-processing, and then the output. Right? And this makes our model definitions a lot simpler and more concise for our machine learning team. So I'll just come back to the notebook and show you once more. So I've got that query, and I can run that query in multiple environments, and also we can look at how that query is represented and serialized. So if I just do, say, query.schema, and you can we can kind of break it down. So it's serialized into protobuf, and it's essentially a tree representation of how we break down this query, right? So you've got the limit as the last operation. So the root node here is the limit, and then it's sort by and the pipeline, right? So you can kind of walk through this and kind of convince yourself, okay, this is a tree representation of this query. And that's how we kind of bridge that gap or that's how we ship the model and the transformations to the online context. Yeah, and these models are also composable, right? So on Tubi, we have something like 30,000 movies and TV series, and on each request, we don't really want to have to rank all of those because the user is not going to browse through 30,000 items, right? So really, it's only the first few hundred or even 1,000 that matters. So we'll have a cheat model we call recallers that grabs a smaller subset of content that we feel the user might be interested in with no relative ordering yet. And then we combine all of those and then feed that into what we call the ranking model, which is more expensive, but it ranks all of the results from the recallers. And then there's a Reranker which are generally specialized purpose models that might be ranking certain containers, or that meets certain specialized business criteria. And we just keep them separated out. So each of those models have the same thing, right? Input, transformation, output, and then we can combine them into a bigger model, which is called the recommender model, which also has input, the transformation, and the output. And this composability allows us to share a lot of these smaller models and components, right? Rerankers that meets certain business criteria might need to be used across multiple recommendation models. Recallers are also useful across different recommender models, so that when our machine learning team is actually writing the full model, it saves them from having to re-implement a lot of these components in the system. Right, so let's continue with this Russian nesting doll, wrapping things into bigger things. Right, so all of these recommender models then roll up into what we call ML applications, which comes with an ML API, a set of models and business logic that defines that defines how to put these model results together, and then all of that wrapped into one service, right? So when you go to tubi.tv in that home screen, that request makes its way to our ML API, which then says, okay, I need to serve a personalized home screen. Give me content rankings, give me container rankings, give me cold start rankings. It goes through the same model, all the same kind of pipelines. And then the business logic is kind of how to put all of those rankings together and into a combined response. So this is where really kind of our Scala and Akka choice of tech stack shines, right? So with Akka, it's very natural. It helps us naturally separate out the concerns of the API layer from the modeling layer to the DB, the database interactions, to the actual business logic, which we'll see some details in a little bit. So one thing here, right, is this need to iterate quickly, right? So machine learning teams might want to change a particular ranking. They might want to run some A/B tests, or they might want to actually change how the business logic works. And so machine learning operations at Tubi has to balance this dual concern, right? We want our production system to be fast and robust and reliable. At the same time, we want to enable our machine learning team to move very quickly, right? If you only have the previous objective, you don't let the machine learning teams run any experiments, right? And if you only have the latter objective, you have a really crappy user experience because you have alerts and downtime all the time, right? So one kind of compromise that we came up with was to control as much of or encode as much of the application logic in configurations, so that it sets, and the configurations set some guardrails for how you can what you can change, the granularity at which you can change things, and how to encode experimentation to override certain parts of that configuration. So what we're doing is separating the serving system from the business logic, so that we can actually satisfy both objectives at once, right? So at Tubi, majority of our machine learning tests require very little or even zero human intervention from our machine learning operations team. So, okay. So, basically what we talked about today is, hopefully I've convinced you that machine learning operations is different, right? Beyond just having more boxes in this diagram, there are also actually important differences. The feedback loops inherent in within every part of this diagram, the gap between research and production, and then the need to coordinate across multiple teams so that we can iterate successfully and iterate quickly, right? And I took you through the journey of how we did the real-time model inference migration. We're also working on some pretty exciting stuff with bandits, especially contextual bandits. And that will also be real-time. It won't just be real-time inference, but also real-time learning as well. So hopefully that will be a talk to be a talk in the short future. All right. Okay, so I guess we didn't run over as I expected, but thank you for listening to my talk, and I'd love to take questions.
Hi, thanks so much for your talk.
Hi.
We have a question to ask you live, and it is, what do you think of the Lambda architecture to organize such a workflow offline and online? Do you think it is still useful nowadays?
I guess, is there a specific aspect of how you want to apply the Lambda architecture? Like, are you talking about like feature? Are you talking about, is that like on the feature store, organizing features, or is it like the model computation itself?
I'm not sure. It wasn't specified, but maybe our question asker can throw something in the chat or in reply to the question.
Yeah, it's a little bit different. So like Lambda architecture can apply in how we process the feature data and do the feature engineering. It's a little bit different from the talk today, which is the real-time model computation. And then in terms of like real-time model computation, people can mean different things. It could be that you have a asynchronous near real-time model computation where this is where Lambda architecture might apply. But for 2B, this application that we talked about, it can't be asynchronous, right? You've got a user that's coming in and needs a response immediately. But I'm happy to talk more details and just ping me offline or something.
Yeah, great. Thank you. Thank you for answering our question. And it doesn't look like we have any other questions at this time. I'd like to invite our viewers, if you have any more questions, please put them in the stage Q&A area, and we'll take note of them and make sure they get answered.
All right, thank you.
Yeah, thank you very much. I hope you enjoy the rest of your day and the rest of ScalaCon.
All righty.